Good afternoon, and welcome to this Johns Hopkins briefing about the James Webb Space Telescope and its science mission. I'm Lainey Rutko, Vice Provost for Interdisciplinary Initiatives at Johns Hopkins University, and I'll be moderating today's briefing. The Webb Telescope is a remarkable feat of science, technology, and human ingenuity. It's the product of international collaboration. It's an effort led by NASA in partnership with the European and Canadian space agencies. It's also the result of partnerships between governments, the private sector, and academia. From the initial conceptual building, the Space Telescope Science Institute, based on the Homewood campus of Johns Hopkins University, has been integral to the Space Telescopes program. The Institute oversees the science and mission operations of the JWST. This coming Sunday marks 9 months since the Webb telescope was launched on December 25th of last year from a European Space Agency facility in French Guiana. Given its ability to observe infrared light, the size of its mirror, and its orbit around the Sun, an orbit that is 1.5 million kilometers away from Earth, the Webb telescope is already dramatically advancing the Hubble telescope's discoveries. When the Webb telescope's amazing first full-color images were released in July, they gave people around the world, including those of us who are not astronomers, a profound sense of the powerful contributions the telescope will make to human knowledge. The release of those images also marked the official beginning of the telescope's science mission, which generated amazing images just this week of Mars and Neptune. I'm grateful to the 3 experts taking part in today's briefing to explain the significance of JWST and to help us understand how it will contribute to a new era of scientific discovery. Joining us today are Dr. Massimo Stiavelli, who has led the JWST mission office at the Space Telescope Science Institute since 2012. He manages 300 scientists, engineers, and technical staff, and oversees the team's strategic planning, priority setting, and interaction with NASA and other partners. Dr. Stiavelli joined the Institute in 1995, and in addition to his work on JWST, made significant contributions to the Hubble telescope. Prior to joining the Space Telescope Science Institute, Dr. Stiavelli was a tenured researcher at Scuola Normale Superiore in Pisa, Italy. He has extensive experience in all aspects of modern astronomical research. Today, Dr. Stiavelli will talk about why JWST was built and what was required to get the telescope ready for science operations.
Thank you.
Dr. Adam, I'm just going to finish introductions and then I'll turn to you. Dr. Adam Rees is a Bloomberg Distinguished Professor and the Thomas J. Barber Professor in Space Studies at Johns Hopkins University. He's also a distinguished astronomer at the Space Telescope Science Institute and a member of the National Academy of Sciences. Dr. Rees's observations of the accelerating expansion of the universe earned him the 2011 Nobel Prize in Physics, and his research contributes to understanding the origin, composition, expansion, and fate of the universe. Dr. Rees and his co-investigators have been awarded time to make observations with JWST as part of their research into measurement of the Hubble constant. Today, Dr. Rees will discuss Webb's first full-color images and what they revealed, as well as how his research will benefit from JWST. Finally, Dr. Susan Mullally is the Deputy Project Scientist for JWST at the Space Telescope Science Institute, and she works to ensure the scientific productivity of the JWST mission. Dr. Mullally is an expert in astronomical time series data collection and analysis and has studied the population of exoplanets in our galaxy and the details of stellar evolution. Prior to her current role, Dr. Mullally worked in the Space Telescope Science Institute's Barbara A. Mikulski Archive for Space Telescopes, or MAST, where she served as lead for archiving data from NASA's Transiting Exoplanet Survey satellite, and also contributed to improving the archiving of data from other missions. During today's briefing, Dr. Mullally will provide an overview of JWST's first year of observations and the future of its science mission. Before I turn to each of our panelists for their initial remarks, I want to remind our audience that we will be providing answers to your questions in real time today. So please submit questions for our experts in the box that you see at the bottom of your screen. When you do so, if possible, please include your organizational affiliation. We'll start by turning to each panelist for a brief overview of key topics, and then we'll move to Q&A. Massimo, I'll turn to you first. Can you please explain why JWST was built and talk about what was required to get the telescope ready for science operations?
Sure, thank you. If we can have the first slide, I'll try in a few minutes uh, to describe the work of over decades of 10,000 people across 2 continents that made it possible to build such a telescope. On the left, you see a diagram showing on the horizontal axis the wavelength of light that JWST covers compared to other great observatories such as Hubble, marked as HST, and Spitzer. And on the vertical axis, we see a schematic representation of the collecting area of this mirror, of the mirrors of these telescopes, how much light they can collect, which is proportional to the sensitivity of these objects. So you see that JWST covers wavelengths of light from the red to the infrared and overlaps in part with both Hubble and Spitzer, but it has a much larger collecting area than those telescopes due to its large mirror. The design requires the telescope to be able to radiate heat in open space, and that's why you see, as you see on the upper right, it has a very peculiar design with a large mirror open and a sun shield that protects the mirror from the heat emanated by the Earth, the Moon, and the warm part of the spacecraft. The diagram in the lower right is a schematic of the orbit of JWST. Around this point, 1.5 million kilometers from the Earth, that remains aligned all the time to the Earth and the Sun. So the sun shield can keep the mirror hidden from those sources of light. And why do we need such a large mirror? Both for sensitivity and for angular resolution. The larger the mirror, the sharper the images you can get. So the large mirror helps not only sensitivity, but also getting very sharp images. And we wanted in the infrared to study objects in our galaxy that are enshrouded in dust, since the infrared radiation can penetrate through dust, but also to study very distant galaxies whose, that have light that is redshifted by cosmological effects more and more toward the infrared, as well as molecules that have infrared lines and can only be detected at those wavelengths. If we can go to the next chart, this is a very quick schematic flow of what happened during the first month of deployment of the telescope. You start from the picture on the upper left, which is what we saw from the upper stage of the Ariane as the telescope was separating from the upper stage of the rocket. And then we start deploying the solar panel, the forward enough components of the structure protected the sun shield. Then we start deploying the sun shield, and finally we move the wings of the primary mirror to their final position. This sequence lasted 1 month, but it was followed by 5 months of commissioning of the rest of the observatory. If we can go to the next chart, I'm trying to illustrate that process. So the first deployments that I just showed are in blue on the diagram in the lower left. But then we had to exactly align the mirror and then to commission, to make ready for science the instruments. And throughout those 6 months, the telescope was also cooling down to its final temperature. So when we launch a telescope like this, the segments are like independent telescopes. So you point to a star and you see 18 separate images that are out of focus, like you can see in the left, in the upper left picture. It, as we capture each segment, we recognize which is which, and we move them into a pattern for convenience. See in the middle, in the upper middle picture, we start to align those segments to each other and put them in focus. In this picture, you see that they are not in focus. Some are much more out of focus than others. And when they are all on focus, you see the picture on the upper right. Finally, you phase all these segments so that their light interferes constructively, combines in a way that gives the distribution of light corresponding not to the sum of 18 1.3 meter segments, but to a single 6.5 meter telescope. And that's the image you see in the lower right. And that concludes my result, because once we get that image, we are ready to start taking real data.
Thanks so much, Massimo. Adam, I'll turn to you. Can you tell us about your reactions to the Webb's first full color images, what's been revealed, and how your own research is going to benefit from JWST?
Sure. And thank you for having me. So I've worked with the Hubble Space Telescope for pretty much my entire career. So that really sets my baseline of expectations. But at the same time, I've known that the JWST was coming. It's been also my entire career that it's been built. So always anticipating and waiting for that. Of course, I knew that it launched successfully. I knew it had been brought into focus, but NASA and the Institute kept sort of confidential the actual images that you could see. So I really saw them maybe only a couple of days before the rest of the public did. And I remember when I saw the first image, and if I could have the first slide, this was the first image I saw. And I was totally blown away. I was not prepared for seeing this. When I first saw it, I really thought it was a simulation, because we've seen so many simulations over the last 20 years of what JWST could do. But the level of detail, and what you're looking at is a massive cluster of galaxies, and you're seeing background galaxies whose images have been distorted, bent by space and time, as Einstein predicted, so that you see this kind of funhouse mirror effect of these arcs and curves. It's kind of an emporium of wonders. And I remember I just got very quiet and just started looking and staring and scanning all over this image, seeing the universe sort of remastered in greater detail than I'd ever seen it before. And this was just about 8 weeks ago. And of course, like any scientist, once I saw this capability, my thoughts immediately turned to what I could do with this telescope, with the science that I do, which is studying the expansion rate of the universe. And I do that by observing certain kinds of stars, rare stars that are buried inside nearby galaxies. And I didn't have to wait too long, only about a month, just a few weeks ago. The James Webb Space Telescope took a picture of a galaxy I had previously studied with Hubble. If I could have the second slide. So this is a galaxy about 60 million light years away. And the squares you see on the left are the regions that I studied this galaxy with the Hubble Space Telescope. And just by luck, for another project, the James Webb Space Telescope observed the magenta rectangle you see on the right. And there's a little bit of an overlap area. And some of those special stars that I use to gauge the expansion rate of the universe are contained in this area. I put some of them in colors so you could really appreciate then. Once we obtained the image from the James Webb Space Telescope, and I could compare the zoomed in versions, if I could have the third graphic here. So the top line is the best we can do with the Hubble Space Telescope. And the circles show, centered in them, the kind of stars that we are trying to measure the brightness of to gauge the expansion rate of the universe. The lower set of rows is each of those same star regions, but now seen with the exquisite resolution of the James Webb Space Telescope. I mean, I can only say this is analogous to if anybody is over age 25 or 30 and remembers when they first saw high definition TV after only seeing standard definition. I mean, it's that big a paradigm change, especially if you're trying to make precise measurements as we are. My colleagues and I have been noting a surprising behavior of the universe, that it appears to be expanding faster than we expect from everything we know. And so we use observations like this to learn about that phenomenon. And the JWST can give us a better view. And so just this week, my colleagues and I put out a first study based on these observations that seem to reaffirm what we've seen with the Hubble Space Telescope, which gets very exciting. And we look forward to many more observations with Webb over the next year. So I'll end there and turn back over.
Thanks, Adam. And finally, Susan, I'll turn to you. Could you explain what will happen during JWST's first year of observations, and then give us an overview of the telescope's science mission going forward?
Yes, thank you so much for having me here. I'll just say, science has really just begun, and Adam just gave a great explanation of his science project and how that's going. We are now 3 months into operations, and much of that data that is being collected with Webb, not all of it, much of it, it ends up in the Mikulski archive and is actually public for most people to use, which means that all scientists can get their hands on these data, and they're starting to figure out how to do the best calibrations and how to make the best measurements from those data. So, we're making these beautiful pictures that the public are seeing, but scientists are now digging in and trying to make precise measurements and seeing really what Webb can do. And so if you show that first slide that I provided, and the middle is actually one of the images from the Webb Space Telescope of a dying white dwarf star that was released back in July. But what you can see from what I'm trying to show here is that we've now completed the circle of all the different things we do that scientists need to worry about in order to get out these science results. They propose for observations, they observe them, it ends up in the archive, they pull that data out, and now they're working on publishing those results. And then eventually those results will feed into the next round of observations. We actually put out a call for proposals to decide what Webb would actually observe over 2 years ago now. And a committee of astronomers went through that open call, went through everybody's ideas and picked out the best ones. And we ended up with 10,000 hours with over 2,500 investigators to make up what Webb would point at in its first year. And that science covers a broad area of astrophysics, from cosmology to galaxy formation, black holes, stars, planets, and even objects in our own solar system, as some of you might have saw with that Neptune image that came out this week. Now, I can't cover everything that Webb's going to accomplish in that first year, so I'm just going to highlight a few. So Webb is, through its imaging and spectroscopic surveys, is going to look at the most distant galaxies we've ever seen before. From that image that Adam put up early on, that was of Webb's first deep field. It's through data like that we're going to be able to look back and see the formation of the first stars and galaxies. There are surveys that are collecting data like this right now with Webb, and be able to really tell us how galaxies first began in our universe. If you go to the next slide, Webb is also going to allow us to study star formation in details that we've never been able to do before. This is actually a picture of 30 Doradus, is also known as the Tarantula Nebula. And this was taken with JWST's NIRCam imaging. And you can see there in the center these massive stars that were born out of this cloud of gas and dust. And it's now some of the radiation is causing more star formation around it. And with Webb, because of that high resolution that Massimo talked about, we can individually make out some of these stars and actually study them right as they're being born. But Webb isn't only going to do the birth of stars, it's also going to look at the death of stars. One of the things Webb can do is through target of opportunity observations, we can actually, with a few days' notice, if a big explosion, for instance, go off and we decide it's really interesting, we can take Webb and go and look at them. And through these kind of observations, we're going to be able to study supernova or even bigger explosions known as kilonova, which is actually where two remnant neutron stars spiral in and collide and explode. And from this, we might learn more about where some of the heavy elements that are common to us around here, where they form, such as gold or platinum. But finally, one of the other exciting bits of science that I'm looking forward to from Webb in the coming year, if you go to the last slide, is that Webb is going to actually be able to look in detail at some of the exoplanets that we have been finding. As you may have known, we've been finding planets around other stars. And the thing is, most of what we know about them is really just their size and how far away from their stars there are. But with Webb, we're going to be able to dig down deeper and really understand more about their atmospheres. And this is through a technique called transmission spectroscopy. And Webb was designed to do these time series observations. And this plot, and excuse me for putting up a plot, but it just shows the breadth of what kind of the variety of exoplanets that Webb is going to be able to look at. You're looking at planet radius on the y-axis and the temperature of the planet on the y. So you can see Earth is down there. And what's really exciting is that Webb is not only going to get these sort of transmission spectra and understand the atmospheres of giant warm planets, but also planets that are similar to the size and the temperature of Earth. And so I've also shown on there the WASP-39 spectra that came out a few weeks ago, where they saw this big hump due to carbon dioxide. These kind of analyses are now becoming easy with Webb, and that's why we'll be able to study those smaller planets, which is coming up soon. And when we can look at the atmospheres of these smaller planets and see, do they look anything like the atmosphere that we have here on Earth, or are they drastically different? And I guess I'll just end by reminding you all that Webb is looking like it's going to have a nice long lifetime. We're expecting it to last for possibly a decade or more. And if with that, it means that we can have many cycles of observations, discovery, and then that will feed back into new ideas. And so it's going to be an exciting time to see what scientists are going to learn with the Webb data.
Thanks very much, Susan. We have lots of questions coming in, so I'm going to transition to Q&A now. And Massimo, I'm going to start with you. Several questions coming in about the relationship between JWST and the Hubble. So specifically, what are lessons from Hubble that help to shape JWST?
One of the first lessons that came after Hubble was repaired and with the Hubble defeat was the richness in morphology of distant galaxies. The fact that we could see galaxies that were very far away, in fact, as far as Hubble could possibly see them, and that they had a lot of structures that needed high resolution, sharp images in order to be recognized. So the idea was immediately to go to a telescope that was infrared, so we could follow them at larger distances, but also that it had in the infrared the same sharp images that Hubble has in the visible, and that requires a larger mirror. So that was the initial driving factor for what became JWST. And then, of course, once you have such a telescope, you realize you can do a lot of additional science. And so that's where we got here.
And Massimo, a quick follow-up from our questions to that. Are there ways in which the two telescopes complement each other or actually work together now?
In principle, there are some fancy techniques where they both could be used to study individual phenomena. This hasn't been attempted yet. The immediate less fancy thing is to just observe the same object in different colors. Since Hubble sees in the ultraviolet and the blue and the red, and JWST sees the red and the infrared. For some objects, you need all of these in order to understand their nature. And then there are other techniques that depend on very precise timing that are being considered now, where you could actually use both telescopes simultaneously to look at distant objects. But this last thing hasn't been, I hope to see it soon, but it hasn't happened yet.
Thanks, Massimo. Susan, question for you, and I'm pleased to say that this is coming from a high school student, so we have a wide range of folks in our audience today. Could you explain what the next destination for Webb will be, or how it's determined what the next focus is going to be?
So we put together a full schedule of what Webb will point at, right? So out of those 10,000 observations, we have to figure out ways to what to look at when, and not everything can be observed at exactly the same time, right? So not everything we observe at any one time. So you have to go through and say, well, this group can be observed now and that group can be observed next. And so we have put together this a long range schedule and then pull things that are observable as we go through. And of course, things like those target of opportunity things, like I spoke of with the kilonova, will change that schedule. And then we have to rejigger what we're going to observe when. So I can't tell you right now. I'd have to go look up what's being observed next week, but that is known. We put together a new schedule every week from what is possible to observe.
Thanks, Susan. Adam, question for you. So Susan mentioned how there was this call for proposals. Can you tell us a little bit about what you and your team, what you had to put together and then submit, and what it was like to find out that you would indeed have time with the telescope?
Sure. Well, it's a competitive process. And so, as Massimo and Susan described, a call was put out for ideas for using the telescope. And you and your team have to write a very detailed plan of exactly how you would use the telescope and what it might teach us, what observing modes you would use, exactly how much exposure time you need, how that time might need to be distributed over the year. And then it's judged by a panel of experts. And we now use a dual anonymous system. So the experts who are reviewing it, they don't know who the proposal's from, and the proposer doesn't know who they are. They just read about the idea, and at some point they make a selection. And generally speaking, both with Hubble and James Webb, we get about 10 times as many proposals as we can actually fill in a year. And so it's really only sort of the cream of ideas that really make it through. So you're very happy if you succeed and get time.
Thanks, Adam. And I guess, Susan, if I piggyback on that, can you speak to what happens ultimately to all of the data that's collected by Webb? And is there some point down the road when it becomes more public access for other researchers who are interested?
Yeah, absolutely. Yeah, the data, gets pulled down off the telescope and processed here at the Space Telescope Science Institute and put into the archive. Each data set has its own exclusive access period for the PIs. We have something like over 2,000 hours of data that's going to be collected in the first year that has no exclusive access. That means the moment it goes into the archive, anyone can go into that archive and pull it down and work with it. I hope everybody gets a chance to go in and get the data. I will warn you, it's in formats that are more conducive for astronomers to work with and not necessarily for the public, but there's lots of tools to figure out how to use it as well. But it means that all scientists, anybody who's familiar with this, can go in and do their analysis. And then even those that have an exclusive access period, it's never longer than a year. So as time goes on, more and more of this data will become entirely public.
Thanks, Susan. With your entry, you have convinced me I will not be personally trying to access this data. I'm happy to learn about it from all of you. Massimo, question for you. In your opening slides, you explained the Webb's mirror, and of course there was a lot of attention in the media about it. Why did there have to be a mirror that unfolded? Would there have been a simpler way to develop a mirror for this telescope?
At the time we started designing the telescope, and in fact, some sense even today, there was no rocket with a shroud large enough to allow us to launch the mirror in a single piece. So we had to design something that would unfold in space. And of course, the same thing happens, even more true for the sun shield, which is about as large as a tennis court. So it's just too big to launch in one piece. So we need to deploy it in orbit.
Thanks, Massimo.
If Artemis launches next week, then we will have a rocket that can launch something like a mirror of that size without deployment.
Of course, our ambitions will grow and we'll want it to be even larger. So maybe not.
Adam, several questions coming in for you related to how how data received from Webb might challenge prevailing theories about the universe. And you mentioned in your opening remarks already one surprising observation, but can you elaborate on that, either what you've already been able to observe or what you think we're likely to learn about?
Sure. I mean, anytime you have a new and more powerful instrument, you have the potential to revise whatever it is that you know. In the case of Webb, through better resolution, sensitivity, greater grasp, going to longer wavelengths. In our case, most recently, as I said, we've been looking at these individual stars in distant galaxies, and we try to measure their brightness. The brightness tells us how far away they are. Obviously, the fainter they are, the further away. And by measuring how far away galaxies are and how fast they're moving away from us, a phenomenon measured by the redshift, we gauge the expansion rate of the universe. In our case, we've been finding this mysterious aspect that the universe is expanding faster than we expect. And so one theory had been maybe the blurrier images from the Hubble Space Telescope was somehow misleading us into thinking that. And so we're doing follow-up studies right now with the James Webb Space Telescope, the first of which we just published a couple of days ago, showing that actually, even with the sharper resolution, we still see these surprising aspects of the universe. There's a lot more work to do on that and many investigations. But whenever you have a new facility, the first thing you're going to do with it is you're going to look at the aspects that were most interesting or surprising, the biggest enigmas that are left over from the previous facility, in this case, Hubble. And so that process is just starting now.
Thanks, Adam. And I'm going to make this next question one where I poll the panel. And again, this is coming from a high school student. What advice would each of you give to a young person who dreams of one day doing the kind of work that you are now doing? And Massimo, I'll start with you.
That's a difficult question. I think being really motivated and interested in something, in our case, science, astronomy in particular, was a big factor, because when one is motivated and really interested, it's easier to deal with all the obstacles that will get in the way. So I think find your drive, your motivation, and pursue it.
Thanks, Massimo. And Susan, I'll go to you next.
I'd say, think big, believe in yourself, and know that, you need to have great ideas, but believe that your ideas are great and push on them. Just like Massimo was saying, you need that drive to get over those hurdles. And so as you have those big ideas, think about what it would take to solve it. And that probably means that you'll need to take a lot of science classes and a lot of math classes. But, also it's important to be able to articulate your ideas. So go take those English classes too and be able to write them down clearly.
I appreciate the plug for a well-rounded individuals. And Adam, I'll give you the final word on this question.
Sure. I mean, I agree with both of my colleagues. I think that if you have a real burning curiosity about these questions about the universe, what's out there, what it's like, that is sort of the raw fuel that you will need to pursue a career like this. But I also want to be honest that there's a lot of math and physics involved. It's not, we're showing you beautiful pictures right now, but the actual understanding and analysis of what we see in the universe involves pretty heavy math and physics. And so you'll want to take a lot of courses in that, and you'll want to enjoy those subjects as well, because you'll be doing a lot of it.
So Adam, I'm going to pick up on what you just said because it speaks to several questions that we've received. Can you pull back the curtain a little bit and explain to us how you go from the beautiful picture that we see as the lay public and then actually analyze it as data?
Yeah, well, that's a really great question. I mean, the pictures that you see, admittedly, we combine multiple colors, filters that are observed individually to produce what is effectively a color image. We, of course, work in the black and white space. And generally, we are using the values or counts we receive in the telescope in each of the pixels to generally make quantitative measurements of certain aspects of what you see in the image, so that it becomes a real process of kind of data analysis, lots of statistics, so that we are measuring certain aspects. We're essentially doing experiments with the telescope, but unlike experiments in a laboratory where you set things up, the universe is just doing what it does, and we're trying to observe it, but we're making that very quantitative. And then we try to take a theory or an idea and we figure out what that theory would predict quantitatively about a certain observation or measurement, and then we measure that from the telescope images. So, it really becomes about data crunching.
Thanks, Adam. And Susan, I'm going to turn to you with a related question that goes back a step even further. How long does it take to receive information from Webb, and to the lay public, what does it look like when information is coming in?
So we sent the data is sent down from Webb from that distant, 1.5 million miles away place called L2. So it's sent down through radio waves to be collected in a big radio telescope, and that happens reasonably quickly. Massimo might actually know the answer for what that time actually is. I would have to do math real quick in my head. Is it?
Yeah, it's of the order of 5 seconds plus
5 seconds.
additional delays with the electronics. But we, unlike in commissioning, we are not talking to the telescope 24/7. Now we usually have 2, we call them contacts a day. So the telescope calls home twice a day. And during those contacts that are typically 4 to 6 hours long, all the data that have been accumulated in the previous hours get sent to the ground at a speed that is 34 megabit per second, which used to be a pretty good speed for home internet a few years ago. Now you can do better than that.
Yeah. Once it reaches the ground, we do all sorts of processing on it. And so it can take like a day or two before it actually ends up in the archive for people to pull down.
If I could add one thing here too, connecting this to the previous question, one of the things that's remarkable about a telescope like this is when we get the images down and we're going to do analysis, we only know so well the sort of calibration or ability to process and get really pure images. And that knowledge improves over the years as we learn more about the telescope. And so researchers like me will need to reacquire their images from the archive every so often to get the latest updates and sort of be able to produce a better and better analysis. So, we don't stop learning after the first image is obtained. We actually continue to improve and learn over the coming years using the same images that we obtained earlier.
This is why it's so important to have a good archive that holds the data for a very long time.
Massimo, a few questions coming in for you. So this briefing is about JWST, but we shouldn't forget Hubble and all of the remarkable work that was done there. So the question is, how much longer is Hubble anticipated to be active, and what, if anything, can you tell us about the rest of the anticipated research program for Hubble?
Well, I can't say too much on that. So Hubble does not have any consumables. So in principle, it can continue working until it breaks. Of course, it has been launched many years ago, but so far there is no indication of any imminent danger. So we expect several additional years of Hubble, getting data and contributing to science in conjunction with JWST. In terms of the science that it does, it works pretty much the same way that Adam described. Every year there is a call for proposal. We try to do them staggered so that the community don't need to write proposals for both telescopes at a time, so to give them a breather. But people write their ideas and they are selected in the dual anonymous way that Adam described, and the best ones get on the telescope. So it's a very similar process.
If I could just add one thing also about Hubble, as Massimo described, we don't know exactly when it will break, but there are a bunch of redundancies in the telescope where you have multiple components that can do the same job. And as individual ones fail, we turn on the backups, and we're sort of down to just about single string, meaning our last version of that component. And so it's a little bit like having, a string of lights. All the lights have gone out and you're down to the last bulb. And that last bulb sometimes lasts a surprisingly long time.
Thank you both. That's a very helpful way to think about this. Massimo, I'm going to come back to you. Of course, lots of interest in the honeycomb design for the JWST. Could you speak more about how you landed on the honeycomb, and maybe what other types of designs were considered?
So I assume this refers to the mirror structure. So the reason, well, it starts out by picking the material, beryllium. When you shape the mirror, it must have an exquisite shape, very precise, to get the type of image sharpness that we want. But we don't know how to polish a mirror at the temperature that they operate. We can do it at the ambient temperature in a normal, factory. So the mirror had to be correct much colder, 40 degrees Kelvin. So, and every material deforms going from the ambient temperature to 40 Kelvin. So we did a study many years ago, and we discovered that beryllium was much more predictable in its deformation than any glass. And that's why we picked beryllium. And then the way the mirrors are manufactured is that we make essentially panels that are about twice as thick as a single mirror, and they are produced with a very specific process that we don't have time to go into. Then they are cut in two halves. Each half will become a mirror segment. And then the mirror segment goes into essentially a computer driven machine that cuts the back. So essentially, the honeycomb is made by cutting away the material that you don't need. And that's done for reducing the weight of each mirror segment. Each mirror segment is like 15 kilograms. It's a little heavier once you add the other structures in the back to control its shape, but they are pretty lightweight.
Thanks, Massimo. And I'm going to stay with you, but I'll invite Susan and Adam to jump in on this one. Can you explain to us at a high level these different organizations that are involved with JWST? So NASA, the European Space Agency, the Canadian Space Agency, of course, the Space Telescope Science Institute. How are they all working together? How do you interface with colleagues at those other organizations?
Well, it was remarkable because they were working together very well. So this telescope started as a NASA initiative, and the European Space Agency, the Canadian Space Agency expressed interest. The Space Telescope Science Institute was involved since the beginning because we were among those that proposed the idea of a large infrared telescope. So the involvement from folks at the Institute dates all the way back to the early ideas. And so NASA has the leadership in developing the program, and then they have contractors that are responsible for each single aspect. So Northrop Grumman was responsible for building the telescope. Ball Aerospace was responsible for the mirror. And we at the Space Telescope are responsible for the operations and both flight and science operations. So commanding the telescope and receiving the data, analyzing them, and so on. So every organization have their own responsibilities, and we have a lot of meetings with each other to make sure we are all on the same page.
Thanks, Massimo. And Susan and Adam, I want to give you a chance to jump in here if you want to add anything about how you may interact with colleagues in these other organizations.
Well, Massimo described the many organizations and their duties in building, but I just want to mention that when it comes to using the telescope, it's an extremely democratic process where essentially any organization, any university from any country or any, even a private citizen can put in a proposal, and if it's selected, use the telescope. And so in that sense, it then becomes wide open.
And I'll just add in those teams, then you have all these science teams around the world that are now coordinating with each other to make the best use out of that data in order to publish their papers and change our understanding of the universe at the end of the day.
And Susan, I'm going to stay with you for a moment. So several questions coming in. If you could explain to a lay person who's enthusiastic to use their own telescope at home, how does what they're seeing compare to the kinds of information that's coming in now from Webb, or even before that from Hubble?
So let's see, compared to a backyard telescope that you might have that you can look through your eyepiece, to me that experience is amazing because you get to put your eye right up to the eyepiece and you see like a little bit of Saturn coming through. That telescope isn't able to collect as much light as Webb. The light you are collecting is all visible light that your eye and body can actually interpret. So whereas Webb is looking out in the near and mid-infrared, so that is entirely different. And then on top of that, because your mirror is so small, you're not getting high resolution, which means that you can't. Two stars have to be farther apart on the sky in order to be able to distinguish one from the other. So like if you think of Saturn's rings, for instance, which you maybe have seen through a backyard telescope, it's so hard these days because people actually are used to seeing all our images from these space telescopes, and that's maybe what comes to mind. But actually, if you go look, it's this very blurry little smudge on there, and it's amazing to see. But if you compare that, if you looked at Saw Neptune's rings and how clear it was to distinguish those two, that's not something you could see through a backyard telescope. I hope that helps.
Susan, and Adam and Massimo, I want to give you a chance to jump in here, maybe from your own experiences over time, or just for those that are enthusiasts in this area.
I mean, the one good analogy I might say is if you've ever looked at the moon with a backyard telescope. You look at the moon through your naked eye, and it's nice, and you see different shades, a little bit of gray. When you use a telescope, suddenly you see the detail of the craters, and it's really probably one of the most magnificent things you can experience with a backyard telescope. That level of detail that you can now see on the moon, those craters, that's pretty much what we're seeing over a lot of the universe with the James Webb Space Telescope. So it's that big a jump for us.
Yeah, and if I can add a little thing, is that if you didn't have a telescope, you would need the eyes at least 6.5 meter in diameter to be able to have a sensitivity that is comparable. But even that wouldn't help because of the infrared, as Susan pointed out, and because our eye is not a particularly efficient detector. So you would probably need to have 30-meter large eyes in order to get the sensitivity similar to James Webb. And then, the same applies, the diameter of your home, backyard telescope compared to that of JWST. And if you're using your eyes rather than, nowadays one can buy a CCD, that would have a much higher efficiency than the human eye. So that would help to bridge the gap. But still, essentially, the ratio of the diameters gives you an idea of how much more powerful JWST is.
Thank you all for weighing in on that one. Massimo, question for you. Actually, it's a composite of several questions. So what we hear through the media is that everything has gone according to plan with JWST, and there were all of these moments at the beginning where everyone had their fingers crossed. So part one is, does that continue to be true, that everything is going according to plan? And then part two is, as time goes on with this mission, what are you most concerned about?
Yeah, I would say that everything has gone better than planned and so things continue to go very well. It's a new observatory, a very complex machine, so we are still learning a few things, like for instance these calibrations that Adam made a reference to. We are still learning how to calibrate the instruments, and this will take a little more time. And But other than that, no, there are no particular concerns. Everything is working very well, and has worked very well since the beginning. Just the one example that everybody more or less is familiar with is that we were designed to carry fuel for 10 years of operation. We probably have more than 20 years of operations on the basis of the fuel, because of the day of launch was very good. The Ariane performance was very good. Our orbital adjustments were very good. Everything was, on the side of being very good. And so the outcome is that instead of 10 years, we have more than 20 years of fuel worth of fuel. And the same is the mirror. It performs a lot better than the requirement. The instruments on average are more sensitive than we thought they would be. So everything has worked very well.
Thanks, Massimo. And Adam, I want to ask you from your perspective as a researcher who has time coming up with JWST, are there particular things that you're concerned about?
Yeah, still space is an incredibly harsh environment. And so this is still a very complex machine with lots of sensitive electronics. And our experience with Hubble and almost everything else we've flown in space is that things do break. Now we have clever backups and clever engineers who can figure out sometimes how to work around those. But sure, you worry about the unknown sort of things that could break. I had a very famous astronomy professor when I was in graduate school who said you always observe the most important things first, because you never know for sure how long your telescope will last, or if a cloud will roll in.
Thanks, Adam. And I'm going to stay with you for this next question that I feel like was tailor-made for you. So we hear with JWST as the lay public that it can see back in time. Can you talk us through what does that actually mean?
Sure. Well, our everyday experience is that everything we see around us is now, just the way it is now. But light travels at a finite speed, an incredibly fast speed, 186,000 miles per second, but still finite. And the distances in space are so vast that there's a significant delay between the formation of an image and its arrival to us. So, for example, when we look at the sun, and please don't look at the sun without glasses or something, but special glasses. But you're seeing the sun the way it was 8 minutes ago, not now. And so if the sun suddenly disappeared, you wouldn't know about it for 8 minutes. Now we look throughout the galaxy at further away stars, and we're seeing them maybe the way they were millions of years ago. And then with a powerful telescope like the James Webb Space Telescope, we can see so far away that we're seeing things the way they were billions of years ago. In our particular case, maybe up to about 13 and a half billion years ago, shortly after the Big Bang. And so by looking out, we look back in time to the time when the universe was younger and when it looked different. And that's what we're so fascinated by using this telescope. We are going to see how the first couple stages after the Big Bang transpired.
Thanks, Adam. You actually answered several of my follow-up questions with that answer. So a lot of questions coming in concerning how you'll know if you're looking at data from shortly after the Big Bang.
Sure. Well, also because the universe is expanding, the further away things are moving the fastest from us. So not only do we take these pictures, but we measure how fast those things are moving away from us, and it serves as a kind of timeline for the universe. So we look for objects with the greatest redshift or apparent motion away from us due to the expansion of space, and that's our metric for figuring out how far back in time we're looking.
Thanks, Adam.
If I could add
Please.
one thing, it's another aspect on top of that, which I'm personally interested in. We know that the composition of the universe after the Big Bang was mostly hydrogen and helium and only traces of other elements. On the other hand, if you look around us in our rooms, you see a lot of, carbon, oxygen, silicon, these things. These things were made in stars. So astronomers call metals anything that is heavier than helium. just for simplicity. So the metallicity, the content of these metals, has increased over the evolution of the universe. And one of the things that we would really like to discover is the first generation of stars that produce the first heavy elements after the Big Bang. The first step, starting from the composition of the universe after the Big Bang and getting to the first elements. And those stars are very we have never seen one. They must exist because there must be something going from the primordial composition to the stars we see today, and those would be a very uh, high prize for somebody. And whether or not JWST can see them is to be, we'll see. It's very hard, but it's not impossible.
Well, thank you so much, Massimo. I think that is the perfect note to end this briefing on, since we're coming up on the hour. So I'm going to thank Massimo Stiavelli, Adam Rees, and Susan Mullally for joining me today for a great conversation. And I'd also like to give a big thank you to everyone who attended this briefing, and especially to those who submitted questions for our experts to answer. A recording of this event will be made available on this website, which is the online home of the Johns Hopkins Briefing Series. Thank you again for joining us today.